The first step in quantitative method development is the optimization of chromatographic method with the aim of separating the analytes and matrix components. We scan both the standard and the sample according to our standard method with the following parameters: 5 microliters injection volume, mobile phase consisting of formic acid and methanol with flow of 1 milliliter per minute and gradient as shown. We monitor several signals, but the most important is at 338 nanometers, and we also monitor signals in MS by using MS to scan in negative mode. If we load our data files, so we will load base peak chromatogram and our signal. We can see that the tried gradient actually shown satisfactory resolution. Both peaks of our analytes, apigenin, glucoside, and apigenin, are clear. In the next step, we will need to select precursor ions for MS2 experiment. We extract the first order mass spectra of both analytes. Of course, we subtract the background. We can see that both compounds give almost exclusively deprotonated ions, and generally in negative mode fewer adducts are observed, as well as fewer fragments, which contributes to better sensitivity. Additionally, both compounds are phenols, and thus they are acidic, and they give stronger signal in negative mode than in positive, which together with lower and cleaner baseline allows for much more sensitive analysis. Several MS-related parameters can be optimized. In this exercise, we will optimize fragmentor voltage and collision energy, while for nebulizer gas pressure and drying gas flow and temperature, we will use values previously found to be satisfactory. The first parameters we will optimize is fragmentor voltage, that is a voltage between the capillary and the skimmer. The standards will be analyzed in MS2 sim mode, so we will only monitor deprotonated ions of both analytes, 269 for apigenin and 431 for apigenin glucoside, at different fragmentor voltages from 110 to 230 volts in 10 volt increments. For both compounds, we will now read peak areas in extracted ion chromatograms. So we have separate chromatogram for every fragmentor voltage. We read peak areas and then plot them versus fragmentor voltage. We can see that with increased fragmentor voltage, the signal intensity rises, then drops again. Namely, as the voltage increases, the ions are accelerated to greater velocities. If the velocity is too low, the ions will easily be deflected by air molecules present in the fragmentary area and lost. At higher velocities, they will be able to push their way through and enter the high vacuum segment leading to the analyzer. However, at very high energies, collisions with air molecules can also result in ions receiving too much internal energy, which leads to their fragmentation and loss of sensitivity, as we can see here. So the optimum for our analytes, estimated from the curves, is about 160 volts for aglycone and about 210 volts for glucoside. The next important parameter is the product ion for SRM transition. The product ion should first provide high sensitivity, that is, it should be abundant. The second, it should provide high selectivity, so it should be as discriminating as possible. Thus, ions with high M/Z and originating from less common fragmentation pathways are preferred. To select the product ion, we first need to record collision-induced dissociation spectra of the analytes. Since the fragmentation pattern depends qualitatively and quantitatively on collision energy, the spectra should be recorded at several collision energies. The experiments are performed in product ion scan mode with deprotonated ions as precursors at previously determined optimal fragmentor voltage and with collision energies in 10 to 40 volt increments range with 10 volt increments. So now we can open our spectra. So in the spectra of a pigeonine 7O glucoside, there is only one abundant fragment corresponding to sugar loss, so to this reaction. So to ensure high sensitivity, we will use ion at M/Z 268. In aglycone spectra, several peaks are observable, corresponding to different fragmentation pathways. However, to ensure high sensitivity, we will choose the most abundant one at M/Z 117. As with fragmentor voltage, we need to optimize collision energy for each compound so as to maximize the sensitivity. The standard will be analyzed in MRM or SRM mode with previously defined precursor and product ions, optimized fragmentor voltages, and with collision voltages in 10 to 60 volt range with 10 volt increments. We can now process our data. So we extract chromatograms for each collision energy. We read peak areas and plot them versus collision energy. As we can see, with the increasing collision energy, the abundance of each fragment is changing, first rising due to increased production, then falling due to subsequent fragmentation. The optimum for our analytes, estimated from curves, is about 35 to 40 volts. And so now we can define the final acquisition method with the optimized parameters for each compound. With our optimized method, we can now analyze both sample and a series of standards, prepare a calibration curve, and read the concentration of the sample. So we will read our data files, integrate them, read the areas of all the peaks, and prepare a calibration curve. As we can see, with the range of concentrations we used, we actually exceeded the linearity range of the method, which is quite common for MS, but fortunately signals for our samples are well within the linearity range, so we can actually just discard the high concentrations. And we get final calibration curves from which we can read our sample concentrations. Alternatively, if we are within the linearity range, we can use just a simple proportion, but with MS, since we usually do not have such clear linearity, it is preferred to use at least calibration curve, if not standard addition or internal standard method.